So, how do we implement the QADT in Java? So, very similar to any other ADT, like the stack that we spoke about, there should be more than one possible implementations for your ADT. At least you can use array, or you can use linked list, or you can use other variants of the basic data structure, like circular array, which we'll talk about either this week or next week. We'll see how the time goes. But the idea would be, whenever you want to declare the stack, the operations for your ADT, you should really use an interface. So that will allow any implementing classes using different data structure to really have a conforming interface or conforming method headers for their implementation. So that's why we actually want to introduce to you the right architecture to really follow, right? So the way we actually implement the queue, from the at a high level, is really the same way how we did it for stack, but there might be some individual implementation details I will actually highlight to you, so we don't need to spend as much time going over this. But of course, you have to study in detail yourself, given that you already understood how we did it for the stack, right? Let's now go over that properly. So we got the queue interface. Again, it's generic, and we got size, we got it's empty, first, in queue, and dequeue. Very similar interface as before, right? You can see we got use generic parameter E over here, and of course we can have different implementing classes for the queue, like how we did it for the stack. And so this will allow alternative implementations to conform to its method headers. That's the really critical point you want to know in order to justify why we need a single interface at the top, and we got different implementing classes at the bottom. In the case of queue, we're going to talk about 3 different implementation strategies at least, right? There might be others you can also explore yourself, but at least we'll talk about 3. We're going to talk about array queue using the fixed size array, and also we're going to talk about something called circular array, which is also array, but we have to be flexible in terms of the indices for the front and for the back. We'll talk about it once we get there. Also generic. And we'll talk about the link queue. And we only explore about the singly linked list in the lecture, but you can definitely think about whether it will help if you actually use a doubly linked list instead, by having the header trailer and also the previous reference. And of course, all of them will actually implement this high-level queue interface, which can be the static type. Meaning that once you declare your variable of the static type queue, you can actually use either this as dynamic type, or this, or this. You got 3 possible candidates, dynamic types. And let's talk about the implementation for the queue using an array. Let's now take a look. So for this array implementation, it's very similar to how we did it in the stack, but there are subtle differences you must note. And we're also using a fixed size array. So that's why you will see some inflexibility in terms of keep queuing into the queue, but at some point you will actually reach that bottleneck about the fixed size. But we'll talk about how we can make it dynamic later. Let's now just go over quickly about the differences you want to watch out for, but also some similarity. We still have the notion about the maximum capacity over here with any arbitrary number. And also we got a generic array over here. And this is something different from the case of the stack. So you can see we got an integer r. Right? So that's about the index of the back or the rear of the queue, right? So if you visualize it, it looks something like this. So think about this is the array, and the way we treat it is we treat the very first element with index 0 as the front of the queue, and of course we may have more elements. Of course, we may not necessarily have filled out the entire array. So let's say we got ... and the last elements of the queue at the back should be denoted by index r. Let me just say r over here. Or you can say conceptually, you're really pointing to this particular index. That's really the back of the queue or the rear of the queue, right? R. You can either think in this way as like an index or like an integer pointer in this way. Doesn't matter conceptually. Okay. And of course, in our case over here, we got 999. That'll be the last index. And you can think about here, this part over here is the contents of the queue up to here, right? The rest is simply not filled in. They might just be either null or maybe just default value for the data type. Okay. And the way we initialize all the attributes is the same as before, right? You can see over here. So these are just the same as before. And of course, the rear will be just -1. We simply have no elements in the queue. And the way we do the size will be the same. The way we do is empty is the same. And what about the first? This will be important because now we are denoting the first element in the array as the front of the queue over here. Right? So that's really important to denote over here. So this part over here is the front of the queue, or the first element of the queue. Whenever we want to dequeue, we want to dequeue from index 0. And you may already be able to imagine why this particular implementation is somehow going to cost something on the performance, as we'll see. Okay. And what about in queue? And for in queue, very similar as before, we simply have two cases over here. If we have already reached the maximum capacity, it's a precondition violation, which simply throws an exception, which is constant time. And also, we're going to increment the size of the rear index, and it will simply joint the element to the back of the queue. This part here is really similar to push. Okay. And what about dequeue? Dequeue is really the difference between the stack and queue over here. If it is empty, precondition violation. Otherwise, what we have to do is conceptually, we have to somehow delete. Right? We're going to take this out to dequeue. However, we're going to shift this particular block over here to the left by one position. And the way to do it is by using a loop. Right? So that's something I can try to maybe visualize a little bit. So if you want to dequeue, basically this is everything in the queue except for the first part. And somehow you want to shift everything to the left by one position. And the way to do it is you want to copy element 1 into element 0, element 2 into element 1, and etc. Right? You're going to use a loop to actually do this shifting. Right? That's something we actually spoke about when we talk about inserting into an array back in lecture number 2. You can refer to it if necessary. Right? So this will be the shift. Right? And we know very well it takes big O of n, right? Because you have to shift almost everything in the queue into to the left by one position because we are removing the first element. All right. So it's exactly this part over here that's actually doing it. Right. So this part here is shifting everything, shifting the second elements and onwards to the left. Shifting second item I put in the quote because officially we don't really have the notion about second or third or fourth or last item in the notion of the queue. We only have the notion for the first element, right? Shifting second item and onwards to the left by one position, right? You can definitely study the detail for the loop. Hopefully that makes sense to you. Right, let's now talk about the running time, right? Now that we know about how individual method works, pretty much similar to the stack, kind of symmetric. But you also need to know the difference. Let's talk about running time. Okay, so let's now go one by one. What about, let's say, the size? The size method, right, is simply just a return. So, big O of 1. What about is empty? Also return some Boolean expression, big O of 1. What about the first? Either precondition violation throws an exception or returning array indexing the first elements. So that will also be big O of 1. What about in queue over here? In queue, either you reach the maximum capacity, in which case throw an exception, or you simply do some simple reassignments or arithmetic. So that's also big O of 1. Right? So far, it's really consistent with the running time for stack. And if you recall, what was the running time for the pop operation, right? Why don't we take a quick look, right? If you go back to the very, very beginning when we talk about the stack, for the pop operation, it's also big O of 1. But is that the case for dequeue? It doesn't seem to be the case because we saw a loop over here, right? So this part here is going to cause the running time to be linear, right? So that's really also a very important difference for you to see. So this will be big O of n, mainly dominated by this block of code to really have to because we have to shift in the entire block over here, starting from the second element to the left by one position. So that's why it's linear, right? So you can see this fixed size array implementation in some way is not very good, because the Q arguably should be one of the most common operation you want to use, just the same as in Q, but somehow it takes linear time every time to really use a loop to really shift everything to the left by one position. We definitely deserve a better solution. There's something called a circular array to make the DQ much easier, so we don't really have to worry about always treating the first elements in the array as the front. There is a better way, a little bit more flexible way of doing it. That's something we'll talk about later. Okay. All right, let me just make a note over here. Over here. Let me just use blue. Okay, so here, to improve this, we need to be flexible about where the front index is. At the moment, the front index is always 0, right? Let me just make a note over here. So this is a front index. I'm just trying to make some connection to what we're going to talk about later about circular array, so you can always remember how we can make a connection, how we can compare different alternative implementations about where the front index is. Okay, and this will be something called circular array. Right, so let me just highlight it. Flexible about where the front index is, and that will be some exciting variance for the normal fixed size. That circular array is also a fixed size array. However, it's more flexible in terms of the front and rear indices. So that's some exciting variance to learn about as well. Okay. Alrighty, let's now go back here, and that's the code we just went over. Let's now see the performance comparison, right? That's something we talk about. Everything is constant except for the DQ, because we have to shift using a loop. And some exercise for you. At the moment, we are treating index 0 of the array as the first of the queue. Would it really help if we try to treat the rear index over there as the first of the queue? Or you can use another index, but my point is, rather than treating this element over here as the first of the queue, is it possible to manipulate the array in a way so that this element over here, the last elements that's being filled out over here, is the first of the queue? Would it help on the performance? That's something I want you to think about as an exercise, right? If you want to have discussion with me, I'm more than happy to engage. Right, so what if the present capacity, preset capacity turns out to be insufficient? That's exactly the point, right? You can see here, this is where the limitation is as well, similar to the case of the stack. So let me also write it down over here. You can see this part over here tells you that as soon as you actually reach the maximum capacity for your queue, you cannot really put in any more elements unless you actually dequeue some elements from there, right? So this will be some limitation. No resizing has been encoded. And that's something we'd like to talk about as well. I can see in the case of the fixed array implementation for the queue, we got two drawbacks. One is about the inflexibility of treating the first elements of the array as the front of the queue, and also the limitation about no resizing. So that's something we'll try to address. So for this one here, we're going to introduce something called like a circular array. And for this one here, we'll talk about some resizing strategy. That's something we'll talk about, right? Later. Right, so you'll be illegal argument exception. The same discussion as before, right? Just constant time to throw the exception. And we'll learn about dynamic array later. Right? And let's now talk about the alternative implementation using a singly linked list. And the discussion will be very similar to before. Let me just use a similar table over here. So what you really want to think about is we got two possible ways to really use a singly linked list. And the critical line to really see is about where the first element of the queue is. Either we can treat it as the beginning of the list, or we can treat the last node in the list as the beginning of the queue, right? So let's talk about strategy number 1, strategy number 2, right? You can see again the same linked list over here. Alan followed by Mark followed by Tom. The same linked list over here. If I said to you this was adopting a strategy number 1, in that case, where would be the beginning of the queue, right? So that would be exactly over here. So this will be the first of the queue. The first of the queue. Of course, symmetrically, this will be the back of the queue. What about strategy number 2? For strategy number 2, this part over here is going to be the first of the queue. The first of the queue. And now we want to think accordingly. Let's say for strategy number 1, if the first of the queue is over here, in that case, if I want to enqueue, of course I should really enqueue in this way, right? And if I want to dequeue, I should really remove the first, like over here, right? I don't need to draw any further, I hope, right? And what about strategy number 2 over here? Given that the last node is actually the first of the queue, in that case, if I want to enqueue, I should really enqueue in the opposite direction, the opposite side of the first, in which case I should really insert add first. But what if I would want to dequeue? Dequeue, I want to dequeue the last node in the list. So that means remove last. As soon as you see remove last, you will know that it's a no-no, right? Remove last over here. We know that for singly linked list, it's actually going to be linear time operation. And how can we improve this? Well, either you adopt strategy number 1, or you can use a doubly linked list, which will give you the previous reference for resolving this issue here, right? This is big O of n. Well, you got two improvement possible. Either use strategy number 1 instead, or number 2, you can actually use a doubly linked list instead. Either way, to actually improve the running time from linear into constant, right? Very similar discussion pattern as we did for the stack. So that's something you already learned. So I don't need to waste your time further. Okay. Of course, still study the detail. Just make sure you really understand everything. Right. Right. So that's about a singly linked list. And let's see. That's the table we just spoke about. And which strategy should we choose? Well, that should be strategy number 1, because that will guarantee we actually don't really that will definitely guarantee we don't really have to use the remove last for the singly linked list, unless you actually adopt either this or this improvement. And so here is simply just a summary about the two strategy over here. And you can see, because we're using remove the last, that will take linear time. And in both cases, we don't really have to worry about resizing, because the singly linked list or doubly linked list, the linked list structure is simply dynamic itself. So we don't have the limitation as in the fixed size array. So we don't need to shift, and also we don't need to do resizing. But we talk about resizing dynamic array later. Right? And this part over here is really about the polymorphism and dynamic binding that we did earlier, right? So I don't need to really trace the code again. We did it completely in the stack example, right? What I want to highlight very quickly is, you can see once we declare the queue as the interface, we can declare that as a static type. And also this will be dynamic type number 1, and also dynamic type number 2, right? So this part over here is really polymorphism, because you can either assign this to array queue, or you can assign this to link queue over here, right? As long as the right hand side over here is the descending class of the left hand side, right? You can see either array queue, circular array queue, that will be left as an exercise for you later after the discussion, and also link queue. Either one of them can be the descending class of the queue, which means they can be the dynamic type. So this part over here, let me just make a note quickly. So this part here is really polymorphism about assignments, called polymorphic assignments, which you learned about in the earlier OOP course. And about which version of the method that will be invoked, you can see these enqueues over here versus these enqueue invocations over here. right? Even though we are calling the same method that's actually declared at the interface level. However, which version are they going to be called precisely, right? We also did the exercise in the Eclipse earlier for the stack example. In this case, it's going to invoke the version in the array queue. In this case, it's going to invoke the version in the link queue, right? So that's about dynamic binding. If you have any doubts, you can definitely refer to the earlier video when we had the discussion for the stack, right? Similar discussion. But if you got any trouble understanding these, let me know, right? And also similar idea for the first, right? So these are also the methods that might have different version, either in the array queue or the link queue. And the next slide is also about the polymorphism and dynamic binding, which we also did the same exercise in the stack example, right? So I'm just going to let you study that, right? Nothing have been skipped, really. You know, I have already did the discussion earlier. Alrighty, let's now move on to the next part. However, I think in the interest of time, I would like to really talk about a circular array properly, so I will really need enough time maybe from next week. So I would say for this week, I'm going to stop over here about the discussion of arrays and about the stack and queue. I think we cover enough items for you to really digest and study. However, I would like to, before I end this week's lecture, I would like to talk about some very important background study which I want to guide you through, which is about recursion.